Our IWCS webinar series event is hosted by the International Cable and Connectivity Symposium. I am Ed Fenton, a cable industry advisor working with the IWCS team. As Sammy said, if you have questions, please use the Q&A box on the bottom right of your screen to post a question anonymously. If you wish to contact the presenter or IWCS after the presentation, you will be given the contact points at the end of the webinar. Please note that IWCS does not distribute the presentation slides from either our conference sessions or these webinars. However, please feel free to contact the presenter directly and they will respond individually to you. Today, we welcome Dr. Tim Goddard of OFS, a subsidiary of the Furukawa Electric Company from Georgia, USA. He will be presenting his paper on development of a totally dry aerial dielectric self-support cable family. Dr. Timothy Goddard received his PhD from the Georgia Institute of Technology and joined the Bell Labs of Lucent Technologies as a member of technical staff. He has been involved in many areas of process and product development in the field of optical fiber cable as the company transitioned to OFS as a subsidiary of Furukawa Electric Company, FEC. Tim currently is a distinguished member of technical staff and director of global cable R&D. In his current role, he supports technology and product development worldwide for the FEC Group Cable Division. Tim, we welcome you to present at today's IWCS webinar series event.
Hey, thank you, Ed, and good morning, everyone. First, I'd like to start off by giving a shout out to my co-author, Rick Norris, and Jack Ledbetter, Jim Parpence, and the whole technical support team who helped us here, and just everyone else within OFS that was a part of this. It's just really a great privilege to be able to come to work with these people every day and get paid for it. I'm really excited this morning to tell you about the development of a new product family based on totally dry technology of aerial dielectric self-support cables. That's ADSS for me going forward. What we'd like to do today is break it up, the talk into really three main sections. First, we'll introduce the product and the rationale, maybe a little history about why we've done what we've done. And then a more extended session, the next three bullets of design and testing to ensure the fitness for use for this product for our customers. And then the last part of the webinar today will be some of the wrap-up and questions. Take your questions. So let's start with a little history. Back in the mid-1980s, our industry deployed a whole series of loose tube cable designs. And 30 years later, this is still the global design platform for loose fiber cables because the design works very well. It's very robust. It protects the fiber, and it's very easy to handle and install for our customers. Now, the very first designs were fully flooded designs. There was flooding compound around the core and filling compounds in the tube in those first deployments. And the reason for that was something we all know. Well, we needed to protect the fiber from water. Water is very bad for optical fiber, both for the glass. The coating systems are hygroscopic. They soak up water. And we needed to physically block water from getting to fibers, either in a break in the cable midspan or in an enclosure access. Now, those first systems of flooding and filling compounds work quite well in terms of our design intent for multi-decade lifetimes. They weren't very good for our customers. When you opened up the cable, that sticky flooding compound was all around the core. You had to clean it and filling. Then you had to, once you cleaned off the tubes, you had to get into the tubes and clean the filling compound off the fibers. And so we immediately began, and as an industry, to start thinking about how we could make these designs easier for our customers to access and install. And the first step by the late 1990s, we had replaced the flooding compound with superabsorbent materials, what we call dry block designs, tapes, yarns, etc. There's a picture, the upper picture on the right shows a water blocking tape under the steel armor, and it worked quite well. They did block water. They were shown to be very effective in the field, and it made it very nice for our customers. So we said, okay, what's the next step? By the early 2000s, within OFS, we were beginning to deploy fully dry designs, no flooding compound nor filling compound in the tubes, the buffer tubes. We initially targeted these at general purpose loose tube cables. I'm talking about cables that you might bury directly in the ground or jet into a duct or maybe even lash to a messenger wire on a pole. And again, this was very well received by our customers. In the next, we introduced this product in 2003. We had introduced a central tube ribbon product in 2001. And over the next 3 to 4 years, the customer base moved entirely within OFS to these dry or fully dry designs because it brought tremendous advantages to our customers in ease of installation and connectorization. So about 4 years ago, we began to ask ourselves within OFS and talk to our customers and ask them, what about an application of a dry design to an ADSS cable? Moving on, next slide. The advantages of such a design were basically that we could make first a lighter cable in terms of weight per kilometer, no filling compound, maybe lighter tube materials. And that lighter weight cable would give us the potential for either longer spans with an existing design or maybe even higher loading at a given span for the design. But additionally, beyond just those performance attributes, we really thought we could bring that ease of termination and craft friendliness to our customer, especially when you're working at height, which is the case many times with these cables. And so we talked to our customers, and they gave us the input that they would be very, very interested in such a design. So what are the potential downsides to such a design? Well, the bottom line is that our ADSS cable system is installed in the most severe application environment that we make a cable for within OFS. And it must be, it has to support itself for a multi-decade lifetime with not allowing much in the way of fiber strain or no fiber strain on the optical fibers. It's got to be able to resist very significant short-term wind and ice loads and vibration, maybe due to both of those kind of things. These cables will be subjected to a very wide temperature range, from very low temperatures to probably relatively high temperatures, especially around hardwares. And then also, and finally, when we install these cables, they can be subjected to a very, very severe transverse loading at turnaround shifts. So as we thought about this, we realized that to build this cable, we really needed to take care and do a thorough job of testing any design that we came up with. So the next step was to look at the design and the laboratory testing. And here are the key requirements that we came up with internally, and it's capturing the voice of the customer, was that first and foremost, these new cables had to have the same form, fit, and function as a legacy gel-filled design. We didn't want any caveats on performance. We didn't want any super special handling requirements. We wanted it to be fully backwardly compatible with the craft and the practice and the hardware. We also wanted to come out with both a short span design or a light duty single jacket design. There's a huge market for that product. But also we wanted to come up with double jacket, maybe longer span cables that could span maybe anywhere from 300 to 500 meters. We decided on using an engineered polypropylene as a tube material for high stiffness and impact resistance, and also to gain the maximum weight reduction that we're looking for in the cable, as well as losing the filling compound. And then finally, we settled on the water blocking means as a thread in the tube. We didn't want to sprinkle powder on the fibers. We didn't want the craft to have to clean the fibers off in any way. We didn't want to have large rovings that had to be cut away and dealt with the cable. We want it to be as craft-friendly as possible. So we made a whole series of cables, 24-position cables, 18-position cables, 12-position cables, 5-position cables. And we went in for step one and did ICEA 640 type testing, GR type testing, where we temperature cycle it between -40 and +70 C, age it, do the same thing with an average attenuation limit of 0.05 dB per kilometer, and then a maximum attenuation limit of 0.15 dB per kilometer. And this is typical data from baseline attenuation at 1550 for a range of cables. And what we can see from this is that the cables are a very good -40 C cable and +70 C cable, as we expected. One of the things we like to do in OFS is understand where the cable will fail at temperature extremes. So in this case, we go on past -40 to -50. We see that it's very good at -50 as well. And we can actually begin to induce attenuation failures due to contraction windows being violated at about -60 C. So we know we have a very robust design here, and we want some of that robustness in given the application environment. There might be some places in northern USA or Canada where these cables may see -50 C one day, and we wanted to be prepared for that. Similarly, in mechanical testing, this is just a matrix of some average values that we would see in max across the cable lines. We tested this full range of impact, compression, twist, flex, cold bend, hot bend. And as we expected, this product line performed extremely well, essentially no change in attenuation during mechanical testing to ICEA 640. It was expected for this product line, something we expected. And then finally, it's an interesting slide. I included this in the IWCS paper. Just a plot of cable strain versus fiber strain for one design that had an MRCL of about 8,900 newtons. We made two tubes, a blue and orange tube, with our incumbent polypropylene material. We call that polypropylene A, but we also tried two alternate polypropylene materials, a B and a C, just for supply security. And interestingly enough, we want to stay below 0.2% fiber strain at MRCL for these cables. And we saw that our incumbent performed quite well, as we expected. The polypropylene B did just fine too, but we were a little bit out with polypropylene C. And one of the key takeaways from this slide is that you have to be careful with polypropylene. PVT is, for the most part, very similar depending on the brand you buy. Maybe not from a processing standpoint, but from a performance and property standpoint. But these engineered polypropylene resins are usually quite special, and they vary from polypropylene to polypropylene, and we need to be aware of that. Okay. So we finished all of the internal laboratory testing, and it told us that this product line was quite stout, and we expected that. We got together in a design review and scratched our heads and said, okay, what's next? And it was very clear in this application environment that that we needed some extended testing. IEEE 1222 gives us some guidance on that, mainly around vibration and hardware. So our next stage of testing was to go into do this work for vibration. So we took a number of cables, I think 6, 12, and 18 position cables, and we ran aeolian vibration testing on the cables to 100 million cycles, and saw no real attenuation change. We were happy. We saw no damage to the jacket, or more importantly, the tubes underneath the jacket in the hardware. We did dual jacket and single jacket cables. And we didn't move the fibers around. That looked good. We expected and hoped for that. Then, changing slides, we galloped the cable to 100,000 cycles. And this is where I had my fingers crossed. As in this design, we have no filling compound to dampen or retard fiber movement in the cable. This is a reverse oscillated lay cable, so we didn't expect any fiber movement, but there's really nothing to keep the fibers other than that lay, SZ lay, from moving around inside the cable. And the galloping results were very, very good. Not only did we not see any fiber movement, we didn't see any loss after the test. That would have showed up in the fiber movement. We also saw no damage to the tubes under the jacket or within the hardware. Everything was very, very clean after the test. So we started to feel very good about this design. And then the final test that we did is something that is near and dear to us within OFS, is what we use in elevated temperature hardware testing, where we take a cable as shown in the setup on the bottom right, and we have 2 cables here, and we take it up to its long-term rated load for 24 hours at 60 C, and we just put a lot of heat on that hardware and the cable underneath the hardware to see if it can hold up to very hot situations. We take the cable back down to 21 C, 20 C, take it up to its MRCL for 2 hours, and then we run it up to failure. And the goal is to see, for us, not a failure at the hardware, but to see failure out on the span. And that certainly did happen, and for these designs, and in fact, the tubes look quite good after this testing. So we stopped. We had another design review, scratched our heads, looked at each other, said, well, we think we've got a pretty good product here, but are we ready to go to the customer yet? And I was in that design review, and I remember people not looking as happy as they should have been, I thought. But we discussed it, and what came out of our review is we really felt like we needed to do some simulated installation of this cable before we went to our customer. And why? Well, we get back to what I started with. This cable is in very, very tough environment, and our installation conditions can be quite challenging as well. I showed a picture of the kind of places these cables go up in. I mean, the longer spans especially, we weren't so concerned about the short span cables, but the longer spans are going to require a high pull-up tension, and we can get very severe sidewall loading on these cables. You know, it's just to be expected that your customers are maybe going to use smaller turnaround shivs than pull-up shivs than you recommend, and you can be putting that cable into a bend radius that is beyond what you specify, below what you specify. And, you know, the remote locations will dictate how these cables go up. Sometimes I've personally been out in sites that are similar to this, where the bullwheel tensioner was right under the pull-up shiv because that was the only place they had to put it. And so you had very severe wrap angles around a very small shiv and a turnaround angle as well, too, going up for about a 500-meter span. And it's just practice. That's what's going to happen. And we wanted to make sure that our cables would withstand this kind of thing. So the last thing we did was to, whoops, 2 clicks. I got, sorry guys. got these things popping up on my screen here. This is not showing up as a picture like it did in our practice session, but it is a picture that shows, if you can see that, us tensioning the cable under a broad range of sheave sizes, wrap angles, and pull-up tensions, and that's detailed in the paper 16.6. And we really tortured both dry polypropylene tube cables alongside our legacy PBT gel cables. And we were very gratified to see that we didn't see any of tube flattening. And in fact, we weren't able to even fail the tubes until the PBT tube fails, where we just ran the cable to failure. So we saw equivalent performance. So to finish up here, we, at that point, felt like we were ready to go in the conclusion. We had designed a cable family that was truly fully backwardly compatible with our existing legacy PBT gel-filled tube designs that we had sold for many years and that our customers had been using. The key thing with an OFS is we do not like to use our customers as beta testers for these products. When we go to them with something new that solves a problem for them, we want to make sure that we have rigorously tested it and know with a high level of confidence that it will work for our customers and we're taking care of them. And this has been a very successful deployment for us. We have deployed products in North America and abroad, and initial response to this product line has been very positive from our customer base. The dry advantages that we saw in the 2000s for general purpose cables really do make a difference for our customers as well. So as I said before, we're very excited about this, and thank you for listening today. Ed, I'm going to turn that back over to you now.
Dr. Goddard, thanks so much for this great presentation. We do have a few questions. I'm going to field them and direct them your way. And I will remind listeners that we have we've got a little bit of time here, so if anybody has not submitted a question yet, please go ahead and do so. We are logging these. I want to start out with the first question. Are there any advantages or operating benefits, such as attenuation, to still using flooding compounds or gel around the core or filling compounds and tubes?
Yeah, for flooding compound, no, I personally don't believe that there's any advantages at all. In fact, you're adding weight in these products, and so I'm a big believer in the dry solutions. As far as an optical performance, that's really specified by the fiber. So no, nothing in optically. Where you can see some improvement in performance with a jelly-filled cable, tube-based jelly-filled cable, is in extremely low temperature performance. And OFS operates in Russia at our OFS SVS1 subsidiary in Voronezh. And they have requirements for minus 60 C, and they've even seen requirements for minus 70 C performance. And in those cases, you can get special jellies that are designed to work in those temperatures. And so that's very helpful in that sense. Thanks.
Okay, great. Thank you. Next, with long-term outdoor vibrations and temperature cycling, could this cause any detrimental physical effects on the superabsorbent tapes or yarns in the ADSS cable?
Right. So on that one, that was what the aeolian and galloping vibration testing that we did was intended to simulate a lifetime with the cable for vibration purposes. When you combine vibration and maybe temperature swings, the answer is really no. The tapes and the yarns they are effectively the carriers for the superabsorbent material. So once you get them in place and they are there, their function has it's finished. Now the superabsorbent powder is there, and it's available should any water blocking need to be done because of a break in the cable or some sort of a path of water to the cable. And a huge amount of testing has been done on the superabsorbent materials, aging them, freezing them, thawing them, flooding them, letting them dry, desiccating them, reflooding them. And they just continue to work over the lifespan of the cable without any issues. Thanks.
Okay, next, what is the relative cost differential of fully dry versus flooded cable designs? Also, what are the installed labor cost benefits of using fully dry cable designs?
Well, as far as the cost of the cable itself, there is some value there. But not a whole lot. This wasn't intended to be a cost down exercise for us. You still have the same fiber, and it still costs the same amount. You still have the same labor cost of putting the cable together. You still have the same materials other than the PBT versus polypropylene tube and the filling compound. So there's really not a huge amount of difference in the cost of these products. The intent was to provide a benefit for our customers in terms of their time to terminate the cables. Now, we do have numbers somewhere, and we will advertise those numbers. But at the end of the day, the people that validate whether that's real for them or not are your customers. If they think that it is real, they will buy it, and they will buy it over a gel-filled design, and that's what we see in the market. Our customers tell us it's very real for them. I don't know exactly what the number is, but they do. It is real for our customer.
Okay, thank you. Next, you did not show any tensile test data. Did you do the standard tensile test to the maximum rated cable load and maximum long-term load? If so, how did the cables perform?
Yeah, we did full testing on every one of these cables. I didn't share a full suite of testing for everything, but these cables were tested and rated to whatever MRCL that we had for the cable design. So yes, all the full long-term and full MRCL testing was done. Mm-hmm. Yeah, but that's just test data that we have internally to rate the cable. Thank you.
Okay, thank you. Next, is there any special requirement for the diameter and thickness of tubes used in the totally dry ADSS cable?
No, that's a good question. Very, very good question. The diameter and thickness of a tube will be specified based on the cable designer's desire for tensile window margin and maximum spans, rated loads. If they, the cables that we have deployed have a 0.5 millimeter wall thickness. I don't mind sharing this. You can find this. You can go look at our cables and see. We're using a 3.0, 2.0 tube, which was the same diameter of our PBT tubes. But there's no reason why you can't do a 0.4 millimeter tube in certain loading applications. If you go to very long spans, then you have to look carefully at that if you're going lower than that. But no, there's no fundamental requirement that says you have to have a certain thing. One comment, now going on a little bit long on this one, but our engineered polypropylene resins display the same or close to equivalent bulk modulus as that of a PBT. So they are designed to work very much like PBT. One of the big questions we had was when you lost the hydrostatic effect of the gel inside the tube, did you start having problems with crushing? Our mechanical analysis told us we were okay, but we did a lot of testing to back that up. Thanks.
Great, thank you. This is the last one I have for now. I'll remind the audience. We've got a couple more minutes. I'm going to throw this last question out there. What is the max span under Nesc heavy loading?
Oh, you know, I don't know the answer to that question, but in our design algorithms, we would probably, for Nesc, and then you'd have to look at sag as well too. What is it? 3% sag? Is it 1% sag? You're going to have to look at height differential. There's a lot of different things, but I'm going to say we're probably in the, and I'm talking off the top of my head, in the maybe 300 meter range to 400, maybe 500 meter at the outside. You're getting into these very heavy and long spans. We actually don't recommend this product line for super heavy, long spans. We just, at that point, you just want the most robust cable you can possibly get. We actually sell a different design for that. Thanks.
Great. With no further questions, I would like to thank you, Tim, for presenting this very interesting and important topic today. Please note the contact points being shown on your screen should you wish to contact Tim after today's event. Each of these IWCS webinar series presentation events are recorded and will be archived on the IWCS.org website. It normally takes up to 2 weeks for these to be posted. The IWCS webinar series will conduct presentation events on a monthly basis. Webinar events will take place on the third Friday of each month at 10:30 a.m. Eastern USA time. Our next scheduled webinar event will be on Friday, April 15th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for the event a few weeks prior. Please feel free to share our announcements with your colleagues so that they can join in and register as well. For over 60 years, the IWCS International Cable and Connectivity Symposium has been the recognized leader showcasing new technologies in cable and connectivity products, processes, and applications. Our next annual conference will take place on Sunday, October 2nd through Wednesday, October 5th, 2016, in Providence, Rhode Island, USA. Please visit our website at iwcs.org for more event details. In just a moment, you will see a brief survey so that you can provide us your feedback and comments on today's event so that we can further improve this webinar series for you. Thank you for participating, and this concludes today's event.